Hello, this video is on integral test and p-series. Now the first thing I'd like to mention here, based on a previous section covered, that the only time we're actually interested in finding out what the sums of a series will be, the numerical value will be for telescoping and geometric series. The rest of the series tests as we proceed through are strictly used to determine whether or not they converge or diverge. We're not going to worry about. Now, sometimes you'll see, if you look at some of these other videos, that I'll use Maple to show that they did sum to a value if they converge, but you would not be responsible for finding that value. It's way too complicated. But for telescoping and geometric, we will. Otherwise, we will not. First test we're going to look at in this series, section is the integral test. So at this point we would have already covered improper integrals in a previous chapter. So that's kind of what we're working with here. And this basically says that f is positive, continuous, and decreasing for x greater than or equal to 1. And then a sub n is also then written as a function of n. We can say that the series from n equals 1 to infinity of an and the integral from 1 to infinity of f of x dx will either both converge or both diverge, meaning that you will evaluate the integral, and if the integral converges, that means the series would have converged by the integral test. And then also, if the integral diverges, that means the series diverges. So the premise of this is not too bad. Now let's look at this example 1 over n squared. We're going to use the integral test to see whether or not that converges or diverges. So write this, so we have the limit as b goes to infinity. Of course, we replace the value infinity with b. So we're basically evaluating x to the negative 2 dx. That's pretty straightforward. So it's negative x to the negative 1. And you don't have to do this, but I used a property from Cal 1 of definite integrals, where if you want to get rid of negatives out in front, you can do that by flipping the limits of integration, because when you flip the limits of integration, that creates a negative. So any negative that you create will get rid of any negative that you have. But if you don't do that, that's fine. I just like to get rid of any loose negatives. So I wrote as 1 over x, got rid of the negative, and then the 1 and the b flip. Now we only have to put the limit here for the b part. When you plug the number in, you just plug it in. So it's 1 over 1, but the limit goes here. Limit as b goes to infinity of 1 over b. That's clearly going to go to 0. So the integral converges to 1. We don't need the value 1 that much, but it has to converge to some value. So it converges. So that means since the integral converges, the series converges by the integral test. Now this is not, I just want to mention this real quick, this is not real critical here. Notice that the integral converged to 1, but the actual series itself, kind of a famous one, it converges to pi squared over 6. Does seem kind of odd how the pi gets in there, but pi seems to show up all over the place, even in non-geometric applications. Mathematician named Euler proved this. You can look at some proofs if you wanted to. It's no big deal. But it shows why pi squared over 6 is the series. Well, the important thing is those aren't necessarily supposed to be the right answer. That's not, I mean, the matching answers. Because one thing to keep in mind, integrals, you're evaluating across a continuous path. It's like if you're going from 1 towards infinity, you're including every real number along the way. A series is a sum of individual terms, like n equals 1, n equals 2, n equals 3. So it's not continuous. It's sort of like adding up a bunch of rectangles, basically areas, rectangles, without it being continuous like this. So that's why those are different answers. You don't have to worry about that. But all it means is if the integral converges to a value, the series will converge to a value, a different value. And so, okay, there we go. That's what I just said right there, and there it is written in green. Now, how about this one using the integral test? And so this integral is not too bad. You just have to realize that u would have to be x squared, because that way the du is going to give you the x on top. And then to take care of the x to the fourth, all you have to do is rewrite that as u squared. And then, of course, du is 2x dx, so 1/2 du is x dx. So the numerator is basically 1/2 du. I'm changing my limits of integration. I find that to be the best way to do the definite integral. Some people, you may have learned how to do it without doing that. That's fine. But what I like about this is when you use substitution for a definite integral and you change the limits of integration, you never have to go back to the original variable again. I like that. Don't have to change it back to x just to put in the original values. Seems a lot more efficient to me. So b, okay, so b makes it b squared. Of course, 1 squared would be 1. So that's my new limits. 1 and b squared. There's the 1/2 from right here. And we have du over u squared over 1, which that's just basically arctan. And so it's 1/2 limit b goes to infinity of arctan of u. And we only need the limit part where we're plugging in the b, so it's 1/2 limit b arctan of b squared minus arctan of 1. Now arctan of 1 will be pi over 4. Now this is kind of interesting. We've covered this in L'Hopital's rule also, and I know it came back up again in improper integrals. But the limit as b goes to infinity of arctan that produces infinity. Arctan of infinity has an answer. It's pi over 2. So if you wanted to go back and look at that to see, why it came out to be pi over 2, you could. But the point is, this does not blow up right here. That produces a value pi over 2. So that ends up being pi over 8. So the integral converges to pi over 8. So if this was an improper integral problem, you'd be looking to get the exact answer. But actually, if you happen to mess this up, as long as you got it, the fact that it converges to something, I'm not advocating doing it wrong, but if you made a little mistake, as long as you got converged, that would be enough to establish this sentence right here. Since the integral converges, the series converges by the integral test. So that's, yeah, there we go. So it appears these are always going to converge. That's not true, obviously. We'll have diverge. Perhaps very soon we'll have diverge. All right. So next one, we're testing 1 over n minus 1. So 1 over n minus 1, we integrate that. That's a pretty straightforward integral. And it just ends up, so there's how you rewrite it properly using the limit notation. So you replace the infinity with b, and limit as b goes to infinity. So you have that antiderivative is going to be natural log, and as soon as you put the b in right here, limit as b goes to infinity of natural log of b minus 1. That's going to go to infinity. That blows up. So once that term blows up, you have a diverging improper integral, which then also means you can say the series diverges by the integral test. So in other words, we use that integral then to prove that the series diverged. Now let's talk about something called a p-series. This isn't too bad. P-series says that if you have 1 over n to the p, so in other words, so the power is treated as if it was in the denominator. So if you have like 1 over n to the 5th, don't try to overthink this, and it doesn't mean n is -5. No, you would treat the p as whatever the power is in the denominator. And for the series 1 over n to the p, it will converge if p is greater than 1 and diverge if it's somewhere between 0 and exactly 1. So n to the first power, 1 over n, will diverge. Now you can pull, and if you, an upcoming section is called comparison of series. If you have like added and subtracted stuff, it does affect it. That's not a p-series. But if you have any kind of multiple, constant multiple, like this 3, it could be pulled outside the summation symbol, and that would still represent a p-series. So the 3 doesn't really ruin it. Now, added and subtracted terms affects it, but not multiplied terms. So it's still a p-series. So in fact, if I scroll back up here to show you this one we did by the integral test, yes, I'm not saying the integral test is always the most efficient. Usually it isn't, but sometimes there are cases where it's the only way to do it, but not here. So this 1 over n squared that we got converging could have been done real simple with the p-series. It's p-series, the exponent would be 2. 1 over n squared, the exponent would be 2. 2 is greater than 1. Therefore, it's just a converging p-series. Back to the video I do on ratio and root test, I kind of summarize some different rules of how the series connect. I'm not sure if I did that in this section, so I'm going to go ahead and just say it verbally now, and then you can look it up later. Let's see. All right, looks like, okay, maybe I didn't say it, so I'll say it now. That any p-series also integral test would also apply to any p-series. Yeah, I'm not saying it's a better way to do it, but it would also, but not vice versa. All integral tests are not p-series, but all p-series would be integrate. So anyway, this is a converging p-series. And what I've done here is use Maple to show that, n, it's got to be, I didn't put 1 over n. 1 over n does diverge. I think I have 1 over n somewhere else in the notes, different section. But you see, I put 1.01, which is greater than 1. It converged, but look at that. I put 0.99. I think I have in this section on series, just the basic series section before this one shows that 1 over n diverges to the first power. But the p-series backs this up now. So n 1 over n will diverge p-series and integral. Put in something less than 1, 0.99. I don't know what floating infinity means, but obviously it didn't produce an answer. And just for fun, I put in the series we just looked at. We are no way responsible for coming up with that 1/30th pi over pi to the 4th. That's not necessary. So let's come down here and take a look at this one. ln of n over n cubed. The integral test works well for this one, albeit a bit messy. This is kind of I guess a good review of integration by parts. So you bring it up, the x up, and of course b goes to infinity, put the b right there. So here's ln of x is du, and then dv is x to the negative 3. So the derivative ln of x, I went ahead and wrote it as just x to the negative 1. Of course, that's 1 over x. It makes it easier when you come over here and you're combining exponents if you go ahead and just call it x to the negative 1. And then the antiderivative of x to the negative 3 would be negative 1/2 x to the negative 2. And let's see what we have. So the first thing we have is u times v, which will be right there. Remember, we don't integrate that part, but we'll integrate the v du. So v du would be these two multiplied together right here. And then I had a minus here, and of course the parts formula right there has a minus. So minus minus makes plus. And I kind of sort of skipped a step here, but in other words, all I did was combine those together to make x to the negative 3, like right here, and then did the power rule again to get 1/2. Well, the 1/2's already there, excuse me. But the antiderivative of that x to negative 3 is the same thing it was right here. Negative 1/2 x to the negative 2. So even though we don't integrate this first part, we still have to evaluate it from a limit standpoint. And so I went ahead and dropped that x down because the first one's going to be L'Hopital's rule. For the second part, you're just plugging 2 in there, so you don't worry about it. You know, you just come up with a number here. That's okay. The whole key is what's going to happen right here. So you end up with ln over x squared, and as soon as you do 1 L'Hopital's rule, you get 1 over x over 2x, and that would x would drop down and give you 1 over 2x squared as b goes to infinity. I guess you know what? I should have the letter b in there instead of x. I'll try this real quick. I'm not using a stylus, so I'll try to freehand this real quick. Okay, now I'm returning from pausing the video, so because that took a few minutes to do that, and would have been a complete waste of your time to watch me do that. But I replaced all these x's with b's it should have been, and then b with an x over here, so now that was a b. So now it's technically proper. So, but anyway, so here's the derivative: 1 over b, 2 b's. That's going to go to 0, and then so that worked. In other words, as far as it meaning not diverged. And then you come over here and you put in, so 1 over b squared, the limit as b goes to infinity, that goes to 0. Well, anyway, with those all going to 0, and not that important that you resolve this exactly, you know, there's what it would be as an exact answer. But anyway, it's numerical, meaning there's no infinities or anything that makes it diverge. So therefore, you can say that series would converge by the integral test. Let's see. Oh, okay, there I put it in maple just to show that I got it right. So there it is. And there's the answer from the actual series itself. But like I said, not important. But the fact that, once again, the fact that the integral converged, that means the series converged. All right, so this is kind of a summary section here, this particular textbook. I like the way they do that. At each section, they summarize. They put questions in there from the section you're in plus previous sections. And of course, then the more you go, then there's more. We'll see more rules you can use for converge and diverge. So let's take a look at this one, and the best way for this one, based on this. So at this point in time, we only know nth term test for divergence, geometric, telescoping, integral test, and p-series. So that's all we have to work with. We've got about 5 more of them upcoming in future sections, but right now this is all we have. So this one's clearly integral, and it falls right into arc-seek. And the key here is that arc-seek infinity converges to a value. Now, at some point, calculators, they may evolve to where, at the time of this recording, I think some of the newer ones might be able to do it, but where they have all 6 of the inverse trig functions in there. But the way to evaluate this at this point in time, to evaluate an inverse trig function like arc-secant, it's not 1 over arc cosine. It's arc cosine of 1 over whatever the value is. So basically, I'm evaluating 1 over b. 1 over b as b goes to infinity. 1 over infinity is basically 0. So that's why I have 0 right there. And then for arc-secant of 2, 1 over 2 is 1/2. So I did arc cosine of 1/2. Yeah, it seems like they would, at some point, they would put all 6 of the inverse trig functions in there, but Seems to make sense. But anyway, long story short, that it converges because of that right here. The limit as b goes to infinity of arc secant of b has a numerical value. And ironically, it's the same value as limit as b goes to infinity of arc tan of b. It's pi over 2, and this one's also pi over 2. All right, let's take a look at this one. That would be a diverging p-series because the exponent's less than 1. And as I said earlier, any p-series is also integral. But notice the example above, that integral test would not be p-series. So that only works one way. This is diverging geometric. Any diverging geometric would also be nth term test for divergence and integral, and a couple more we're going to use later. So in that section, like I said, on the ratio and root test, it kind of summarizes all of this. The difference here is converging geometric will also be integral, but it won't be nth term test because the nth term test is only a test for divergence. So therefore, it would not apply to a converging geometric. Now this one, nth term test would apply because the limit of ln of n as n goes to infinity would be infinity. So that's has to go to. In other words, if it goes to anything other than 0, the series will diverge. That's what the nth term test is. And integral works here also too. Now one thing I don't think we can say, I don't think you can say that any nth term test is also integral test. I don't think that's right. It's not. It's common for them to be together, but I don't think that's. I don't want to say that exclusively and then be wrong. But integral test would work here because you could integrate that by parts. Oh, here I'm saying if p series or geometric applies, then the integral test will apply. Okay, then so that's what I was just. Then diverging geometric will also then diverge by the nth term test. Okay. All right, so that will conclude this video on integral test and p-series.